To move from functions, which we went through linears and quadratics and cubics and exponentials and logarithmic functions, into two of those functions in particular, logs and indices. Okay, we're going to study those in detail, and we're going to take a look and see, first of all, how they're opposed to one another. What I mean by that is that they're inverse, they're natural inverses of one another. So if you take the logarithmic function and an exponent function, or an exponential function as they call them, they are naturally inverted. In other words, if you use them together, chances are they're going to cancel, providing that their bases match. That's something we look at later on. You'll notice what I've said down there, two words: indices and logarithms, inverse functions. Okay, so we really are hoping that you'll remember everything we learned in relation to inverse functions from the previous chapter, along with what we learned in terms of the exponential functions and the logarithmic functions. Carry that with you into this chapter, where we're going to look at indices and logs in a little bit more detail. Now, I suppose from your junior cert, if you were to talk about an indice, what is an indice or an index? Indices, I think, is plural. An index is a power, okay? And a power is an exponent. So you've got three words. You've got the exponent, you've got the power, you've got the index. They're three different words for exactly the same thing, and they're interchangeable, okay? So when you talk about an exponential function, you talk about a function where the x is in the power, okay? Where the, as we would call it on your calculator, where the alpha x is, the actual x that does the transformation of the domain into your range, okay? So indices, exponents, and powers, they're all the same thing. They are the numbers, or they are the variables that sit on top of a base. So if you take something like this, 8 to the power of 2, how do I describe that? I would describe that as base 8 with the exponent or the power or the index 2. Okay, so you've got to understand that to every number in that form, there are two parts. There's the base part, which is extremely important, and we'll talk, most of this chapter will be based around the base. And we've got the power, the index, the exponent, which is simply a statement of how many times the base is multiplied by itself. So if you take, for example, b to the power of 5, that just means that b is multiplied by b 5 times. The number 5 doesn't come into the multiplication. Now, a lot of people get that mixed up. B to the power of 5 is not 5b. B to the power of 5 is b multiplied by b multiplied by b multiplied by b multiplied by b. Okay, 5 to the power of 2 is 5 multiplied by itself twice. So the power, or the exponent, or the indice, it's basically a statement as to how many times the base number is multiplied by itself. Okay, when did we meet them? We met exponent forms, we met exponential forms in junior cert when we were dealing with scientific notation. Now, scientific notation these days is quite simple because your calculator will do the transformation for you. But basically, scientific notation was a way by which we could write very, very big numbers or very, very small numbers in a reasonably manageable form. All right. If you take that wonderful thing that happened over the last couple of days, where the new rover was placed onto the surface of the planet Mars. Now, if we're dealing with the distance between Earth and Mars, you're dealing with several million kilometers. So therefore, scientific notation makes the whole speed, distance, time relationship an awful lot easier to deal with, okay? So likewise, if we're talking about the breadth of a human hair, or we're talking about the size of an amoeba cell, well, then we're dealing with something very, very small. So scientific notation was a manner that was devised in order to deal with numbers that were very, very big or very, very small. And the key thing that you should have brought with you from junior cert is this. If I was to give you 2.3 by 10 to the 37 and 4.2 by 10 to the minus 17, and I was to tell you just off the top of my head, one of them represents the distance between Earth and Pluto in kilometers, one of them represents the size of an amoeba cell, okay? Which is which? Straight away, I hope you understand that 10 to the 37 is massive, okay? And 10 to the minus 17 is very, very small. So therefore, the bigger the index, the larger the number. The smaller the index, the smaller the number. It's as simple as that, okay? And keep that in your heads as we go forward. It's also used, as I said already, to notate the number of times a value is multiplied by itself. Now remember, base and index, base and power, base and whatever you want to call it, yeah? The power is a statement of how many times you multiply the base by itself. So in this case here, if you had 5 to the power of 4, that is 5 multiplied by itself 4 times. 5 by 5 by 5 by 5. Okay? And in fact, something which I hope you start to get your head around as we go down through this chapter. If you multiply 5 by itself 4 times, what you're really doing is multiplying 25 by itself twice. That's 25, that's 25. So you could actually say that 5 to the power of 4 is the same as 25 squared, which I hope you might have come across a few times in your junior cert, and you know is 625. So there's little shortcuts in there, but the key thing is to get these shortcuts to work for you, you need to practice, practice, practice. You need your tables at your side in order to take the indice rules, and you need to know what rule to apply in a given situation. Okay, what are exponential functions? So we've had this already. Exponential functions are functions where the input is in the index, okay, or in the exponent, in the power. So 2 to the power of x, 3.5 to the power of 2x minus 1. If the variable is in the power, then it's an exponential function. And we've dealt with these already in the previous chapter. A function of the form a to the power of x. So when your variable is in your power, it's an exponential function. Where a is a positive constant is called an exponential function. And just to show you what we've already met in the previous chapter, if the base number is greater than 1, we're going to have rapid growth. Okay, so it's like, for example, 2 to the power of x, 3 to the power of x, even 1.5 to the power of x. If the base number is between 0 and 1 exclusively, yeah, that means you can't use 0 as a base number, and you certainly don't use 1 as a base number. I'll explain why in a moment. Any value between those, which are basically all your fractions. If your base is a fraction, then you get what we would call here exponential growth downwards. So still growth, but it's growth downwards, negative growth. Okay, so this one here gives me positive growth, whereas this one here would give me what's called decay, which is negative growth. Okay, so things like, for example, the half-life of a radioactive substance, they're always a decay function. All right, and there's a function behind every radioactive substance that allows you to track their decay from being radioactive to non-radioactive, and they all follow this particular format. They all follow the decay exponential function. Whereas this one here would be something like bacterial cells growing, or human population growth, or even the investment of money under compound interest. They all have this type of upward growth in terms of their exponential function. Now, one thing I did say to you, if the base number is greater than 1, you get exponential growth. If the base number is between 0 and 1, without being 0 and 1, you're going to get decay. Okay? What would happen if the base number was 1? Now think about that for a moment. What happens with 1 to the x? If I change that value of x for any value off the top of your head, what's the answer? The answer is 1. 1 to the power of 1, 1. 1 to the power of 10, 1. 1 to the power of a million, 1. So therefore, what happens when the base number is 1 is we get a flat line. Okay? So exponential growth with base numbers greater than 1. Exponential decay with base numbers that are between 0 and 1 exclusively. And flatline function when your base number is 1. Now, we're not going to meet this very often for that particular reason. Okay? So I just want you to notice the two types of exponential graphs we have, the growth graph and the decay graph, which are both exponential functions based on having a base that's greater than 1 or a base number that's in between 0 and 1. So let's take a couple of examples and work these things through. Work example 7.1, page 177. It is done in your book. I'm just going to do it here just in order to make sure that we understand how these things are done properly. Graph the function f of x equals e to the half x, starting at minus 4, going to 5, both of them included, and elements of real numbers. Okay, now the very first thing you've got to do is to know how to use your calculator to get that table going. So I'm just going to pull up the calculator here now, and I've learned this already. Let me just see if I can do this. Tab. Where are we? There we are. There's my calculator. So let's just put this in, e to the half x. Okay, bring it over here so I can see what I'm doing. E to the half x. Now, the first thing we've got to do in the calculators, yours works very, very similarly to this. I know yours is probably like my one, okay? But these are the new version of the same calculator. So if I want to put in e to the half x, the first thing I've got to do is locate the exponential function. And there it is, just above the natural log. So if I want to put in e to the half x, the first thing I've got to do is I've got to turn on my function. So menu or setup, 3. Now you've got your f of x. Now it's going to wait for you to put in a function. Notice that when you want to put the x in, it's an alpha x. So you press Shift E. So there's your exponential function. You want to fraction in, so you press the fraction button. 1 over 2. And after the half, it's alpha x. Okay, so there's that function there on the screen of your calculator. Press equals. Where we don't want a second function, no, so we'll skip that. Now where do I want to start? I want to start at -4. I want to end at +5, and I want to go in steps of 1. So there we are, there's my table. So you'll notice now you've got -4.1353, so on and so forth, -3, -2, and then we have all the way up as far as 5 itself, which goes up to 12.182. Now you take those values and you draw out your table. So once you use your calculator to get your table, you draw your table, and your table comes out to be something, I'm going to do that, your table comes out to be something like this. There it is. Now I didn't put in 5 into this one because I wanted to just keep it flush with the question above, so don't worry about the 5, doesn't matter. -4.1, 4, 7.4. So I'm being told to graph. Now when you're being told to graph, you've got to be careful. You've got to use graph paper. You've got to make sure you're using the right part of your XY axis. You've got to label your X axis, label your Y axis. So check the X axis. We're going from -4 to +4. That's symmetrical. So we're going to be going something like this. Okay. And then on the Y axis, we're going from 0.1 up to 7.4. There's no negative Y's. So you can put your Y axis there like that, and your X axis here like this. There's 0, there's 4, there's -4, there's 8. And then you very, very carefully break up those axes into usable sizes that you can plot your points on. Now, because obviously I can't do that here, I have the graph already done. And here it is. Okay, so there it is. Okay, that's your graph. Now, what they're asking me to do here, after I've drawn my graph, notice, by the way, X and Y, you've labeled your graph. You've got to be very, very careful. Label your axis, X and Y, and make sure you get the best curve you can through those points that you plot. Part 2, use your graph to find an approximation for f of 2.5. Now look, f of 2.5. Numbers in the brackets are your domain values, and your domain values are your x values. So what they're saying here is that you've got to go to the x-axis, find 2.5, draw from 2.5 upwards until you hit the graph, then you immediately turn 90 degrees, like this, and you end up getting your answer as being about 3.6 or 3.7. So f of 2.5 approximately, and even if you want to do this, look, show you now, if you want to do it this way, you can say approximately equals, use the wavy lines, it's approximately equal to about 3.6. Okay. Part 3, use your graph again to solve the equation f of x equals 4. Now please remember, x is your domain, 4 is the output, 4 is your range value, and your range value comes from the y-axis. So this time you're going to 4 on the y-axis, you're going to draw across until you hit the graph, like that, and when you hit the graph, you're going to drop down a perpendicular. And you're going to hit the x-axis, x equals, what's that, about 2.75, about 2.75. And again, the more accurate your graph, the more accurate your answers. So be careful that you understand how to carve up your page, and the full page, don't use a quarter of the page, use the full page, draw your graph properly and fully, and then extract the answers as asked in the questions. So I'm just going to leave you with 2 of those to do yourselves. You can pause this now, you can go to page 178, you can work on question 6 and question 9. You will need graph paper. They're very, very simple to do, but it's just a refresh of how to draw these exponential functions and what they look like and how we can extrapolate information from them. So pause them and off you go. Now, we've got laws. So exponents are governed by laws. Okay. What does that mean? There are rules to apply. Okay, the lovely thing about the rules is that they're in your tables. Every law that you need in order to get through any exponential question is in your tables. In fact, on page 21 of your tables, along the left hand side of your page. I'll show you them here in a moment. The laws of exponents, also called the laws of indices or the rules of indices or the rules of powers, doesn't matter what they're called, they come from three ideas. Okay, the first idea is that if your exponent is positive, then it simply tells you how many times you're multiplying the base number by itself. So for example, 6 to the power of 3 means 6 by 6 by 6. Notice that the number 3 never appears. 3 is not a number, it's a statement of how many times you're multiplying 6 by itself. So 6 by 6 by 6, which is 216. So that's the first one. If the exponent is positive, you're going to get growth, okay, by multiplication. Now, what's the opposite to multiplication? If a positive exponent gives you multiplication, what's a negative exponent going to give you? And the answer should be staring you in the face. It should give you division. And it does. Watch. A negative exponent means that you divide by that multiple. So in other words, if I have 6 to the minus 3, it can be taken as 1 divided by 6 to the 3. So because a positive exponent involves multiplication, a negative exponent will always mean division. So when you get a negative exponent, you will always be forming a fraction with the numerator 1. Okay, now that's extremely important. If you can get these three ideas into your head, then you're going to fly through these exponents, because at the end of the day, the 10 rules we have are rules that just show you what to do with positive exponents, negative exponents, and the third one, which you'll look at in a few moments, fractional exponents. So positive exponents, what do? They increase in value through multiplication. Negative exponents, they undergo division. And again, if you remember, addition done quickly is multiplication. Subtraction done quickly is division. So therefore they are related intrinsically to one another. So positive indices will give you multiplication. Negative indices will always give you division. So let's just take a look at a few of these. What's the value of 6 to the 3? Now, 6 to the 3, what does it mean? The power tells me how many times 6 is multiplied by itself. So that means 6 by 6 by 6. And 6 by 6 is 36, times 6 again is 216. You can do it on your calculator, it's quite easy. Next one. What is the value of 2 to the minus 4? Now, notice that my exponent, my power is negative. So that means that I'm going to divide 1 by 2 to the 4. Because the negative exponent automatically brings in division. Okay, and that's going to give me 1 over 2 to the 4. 2 to the 4 is 16. That's 1 over 16. And if you want to go to your calculator, 1 divided by 16 to find out what the answer is 0.0625. There it is there. Answer C. Okay, so just keep that in mind. A positive exponent, multiplication. A negative exponent, 1 over the multiple 2 to the 4. It'll always give you a fraction. Next one. What's the value of minus 3 to the power of 5? Now, this is called indices. This chapter is indices. Okay, so you're looking at the power. The power is positive. So therefore, in this case, this is minus 3 by minus 3 by minus 3 by minus 3 by minus 3. It's minus 3 multiplied by itself 5 times. Positive exponents, positive powers tell you how many times to multiply the base by itself. Key thing here is that if I multiply, I would do the minuses first. Minus by minus is plus. By minus is a minus. By minus is a plus. By minus is a minus. So therefore you've got a minus answer. Okay? And you've got 3 3's, which are 9. Another, that's 9. That's 9. And 9 9's are 81. And 81 times 3 is 200. Let's check now. 81. Oops. 81 times 3. I don't want to be taking any guesses here. 81 times 3 is 243. 243. And there it is. So again, what did I do? I grouped. I did all the negatives first. You've got an odd number, an odd amount of negative numbers. If you're multiplying an odd amount of negatives, the answer will be negative. The only time that you will have a positive answer when you're multiplying negative numbers together is when there's an even amount of them. Here I've got 5 minus 3's. So that means you're multiplying minus 3 by itself 5 times. Because there are 5 minus 3's being multiplied, the answer will be negative. And then 3 by 3 is 9. 3 by 3 is 9. 9 9's are 81. So it comes as 81 times 3, which is 243. Just break it up. Make it easy for yourself. Or, of course, get the calculator and get the answer. You're not told you can't do it in the exam. You can. Nice to be able to do it in the head, but. Second one. What's the value of minus 5 to the minus 3? Now, check your power. What's your power? my power is negative. So immediately, negative powers give rise to division. 1 over minus 5 to the 3. See? So the negative power is 1 over the multiple. That's what you got to remember. Which comes out as 1 over, now look, you're multiplying minus 5 by itself 3 times, so it's going to be minus. 5 5s are 25, times another 5 is 125. And there's the answer there. That's it. Okay. Last one. What is the value of 5 squared plus 6 squared? Now, I want to point out something here. The base numbers, 5 squared and 6 squared. There's a golden rule which you may remember from your junior cert, which states that if the base numbers that you're using don't match, then you simply have to take each term on its own merit. So that means that I can't do anything collectively in this question. I have to do it individually. 5 squared, 25. 6 squared, 36. 36 and 25 and 36 is 61. Part C, that's the answer. Okay, now I've picked these questions here from an online course on indices. I'm going to ask you in your own time when you get these slides to press that link at the bottom and to go in. There's 10 questions. I've done 5 of them. There are 5 left for you to do. Just practice how to use the positive indices, which is a multiple, negative indices, which is division of 1 by that multiple, okay? And then if the base numbers don't match, you take each one separately, work it out for what it's worth, and then do whatever you're told to do in that particular question. So what are my laws? Now, the third thing that we're talking about, we said there's 3 things that our laws are built on. The first one is a positive index, multiplication. The second one is a negative index, division. The third one is a fractional exponent or a fractional power. And fractional powers always mean a root, okay? So a fractional power of a half, and you know this already, x to the power of a half is another way to write the square root of x, square root of x, okay? Pin, square root of x. X to the third is the cubed root of x. X to the fifth is the fifth root of x. So in other words, when your exponent is a fraction, you will always be using roots. And the family of fraction that you're dealing with will be the root that you've got to engage. So if you're using halves, it'll be a square root. If you're using thirds, it'll be the cubed root. If you're using quarters, it'll be the fourth root. If you're using tenths, it'll be the 10th root. So you've got to understand that the fraction in the power, the family of the fraction you're dealing with, will always tell you what root to engage. Okay, so if we take a look at this question down here, what is the value of 25 to the half? Now, what's the family of the fraction that's involved in the power? They're halves. So halves involve the square root of 25. And the square root of 25 is 5. That's how easy they are. And that is the third, the third idea that these laws are expressed on. Let's try another one. What is 256 to the power of 3/4? Now, first of all, look at the power. The power is fractional. You're going to be involving roots, okay? What is the family of fractions involved here? They're quarters. So you're going to be involving the fourth root. Now, what about the 3 on top of that? That stays with the 256. So in other words, 256 to the power of 3/4 is the fourth root of 256 cubed, which your calculator will very, very easily give you. So we get the fourth root, shift fourth root of 256 cubed, and you just press equals and you get an answer of 64. Okay, so don't be afraid to get your calculator after you have turned it round to make it easier to deal with. Next one. What is 1024 to the power of 2/5? Question. What's the nature of your power? It's fractional. Fractional powers involve roots. Okay. Now, what's the nature of the root? Well, what's the family of fractions we're using? We're using 2/5. So the family of the fraction is the fifth. Okay. So therefore, it's going to be the fifth root. The fifth root of 1024 squared. So you only look at the bottom number of the fraction that's in the power. because that will tell you what root to use. And you leave the numerator of the fraction with the base number. And again, your calculator will tell you quite quickly that if you put in the fifth root, so the fifth root of 1024 squared, the answer there comes out as 16. That's it. So, 3 ideas. Number 1, is the power positive? Yes, multiplication. Number 2, is the power negative? Yes, division. 1 over whatever the multiple would be. Number 3, is the power a fraction? And if the power is a fraction, you will always be using a root. And the value of the root that you will use will be the same as the nature of the family of the fraction. If it's halves, it's square root. If it's quarters, it's the fourth root. If it's sevenths, let's say if it was 4 over 7, then you'd be dealing with sevenths, so you'd be dealing with the seventh root. Okay, so keep that in mind. Next one. What is the cubed root of 8 over 27 to the minus 2? Now, there's a lot going on here. Okay, this is where you begin to see things coming together. First of all, we've got the cubed root. The cubed root is related to the power being in thirds. Okay, so that means I could write this straight away as 8 over 27 to the power of minus 2 over 3. Because the cubed root means that the fractional power would be a third, okay? And because there's already a minus 2 there, it comes minus 2 over 3. Now, let's do this carefully. First of all, if I want to get 8 over 27 to the power of minus 2 over 3, I will take top and bottom separately. So I'm going to take, first of all, 8 to the minus 2 over 3. Let's see what that is. What's the cubed root of 8? The cubed root of 8 happens to be 2. So that becomes 2 to the minus 2, which, as we've already said, is 1 over 2 squared. So there's the top one done. Take the bottom one. What's 27 to the minus 2 over 3? Well, again, as we told you, the cubed root of 27 is 3, and 3 squared is 9. Or you can do it this way. The cubed root of 27 is 3. 3 to the minus 2, which becomes 1 over 3 squared. That means 1 over 4 is on the top, and 1 over 9 is on the bottom. So what I've done is I have simply given that power to the top and the bottom. Okay, 8 to the power of minus 2 over 3 is going to be a fraction because negative powers always involve division. Okay, so there's your fraction. The power is also a fraction representing the family of thirds, so it's going to be the cubed root of 8, and the cubed root of 8 is 2, and then 2 squared is 4. So you've got 1 over 4 divided by 1 over 9, but I hope you remember, you can't divide by a fraction. You've got to take this fraction here up and multiply it by its inverse. See that? So the answer comes out as 9 over 4, which is 2 1/4. That one there. Okay, so they are getting a little bit more tricky as they go on, but that's what you can expect at this level. Next one, 64x cubed divided by 27a to the minus 3. Now again, take each term separately. Let's take the 64x cubed, first of all, on its own to the minus 2 over 3. Okay? The one thing you'll notice is this. We're getting the cubed root of 64, and then you're also getting the cubed root of x cubed. So there's two parts to this. The cubed root, because we're dealing with the power of a third, minus 2 over 3, so the family is a thirds, so it's going to be the cubed root. So this becomes the cubed root of 64x cubed to the minus 2. See that? She leaves a minus 2 in with that afterwards. Now, what does that become? What's the cubed root of 64? The cubed root of 64 is 4. The cubed root of x cubed is x. And that's to the minus 2. Negative powers will always involve division of 4x to be squared, which comes out as 1 over 16x squared. And that's your answer. 1 over 16x squared. Or say 9, I should say. Is it 9 over 6? No, 1 over 16. Oh yeah, that's the first part. That's the top part. Bottom part, you now have to take your 27a to the minus 3. And you're going to raise that to minus 2/3. Okay, first of all, we're dealing with a fraction in your power. The bottom of the fraction is 3, so it's going to be the cubed root of 27a to the minus 3 to the minus 2. So let's do this. Cubed root of 27, 3. the cubed root of a to the minus 3. Now just be careful with that. A to the minus 3 is 1 over a, all raised to the minus 2, okay? Which is 1 over 3 over a to be squared, which becomes 1 over 9 over a squared. It's 9 over a squared. Now again, division by fraction, it'll be a squared over 9. So if I'm going to divide this term divided by 9 squared, or a squared over 9, I have to turn the second thing round, and I'm going to get 9 over 16 x squared a squared, or a squared x squared, put them in alphabetically. Okay, so you get 9 times 1 is 9, and then bring the a squared down here in front of the x squared, and that's what you get. And the answer is 9 over 16 a squared x squared, this one. Again, there's more practice there if you want to use them, but keep in mind, they're all based on 3 ideas. Positive power, multiply out. Negative power, 1 over whatever you would get when you multiply out. So it's division primarily. And if it's a fractional power, look at the nature of the family of the fraction, see what the family of fractions is that you're using, and that is the root that you're going to use with that particular base number. Okay. Now, what are the laws? Well, look, I've broken the laws down into this table here with a couple of examples, and then beside that, that's what's in your tables. Okay, now I'll come back to that in a moment. I don't want that just yet. So I'm just going to deal with these ones. Any number to the power of 1 is itself. Okay, just keep that in mind. If you raise anything to the power of 1, it remains exactly the same. Any number raised to 0 is automatically always 1. And these are things we have to watch out for. All right, so any number raised to the power of 0 is 1. Remember what I told you? If you've got a negative power, it means division. So x to the minus 1 will become 1 over x. 1 over x. It's like that. So the negative power always means division. Negative powers always mean fractions. And by the way, fractions always mean negative powers. They can go backwards as well. Notice the next rule. Now, this is what we call the multiplication rule. If the base numbers match, the base of m is x, the base of n is x. If the base numbers match, you keep the base number and you add the powers, because multiplication and addition are intrinsically related. So for example, x to the power of 2 times x to the power of 3, you keep the x and you add the 2 and 3 to give you 5. Okay? If multiplication of similar bases leads to the addition of powers, then we can say division of similar bases with different powers will lead to subtraction of the powers. So x to the m divided by x to the n will become, keep the base again, and subtract m minus n. And here's an example. X to the power of 6 divided by x to the power of 2. Keep the x because it's the same base. Subtract the powers. You get an answer, x to the power of 4. Next one, and this is an easy one to remember. What do brackets mean? Brackets mean multiply. Okay, and brackets normally always go in between the two numbers that you're going to multiply. For example, if I gave you something like that, you'd know exactly what to do. You'd multiply the two that are separated by the bracket. Here, you do the same thing, but notice what the bracket's going through. It's going through the m and the n. So therefore, x to the m, all raised to the power of n, you keep the base number and you multiply the two indices. So for example, x squared raised to the power of 3, keep the x, multiply 2 3s, you get x to the power of 6. If you have a product, different bases, raised to the power of n, you just give both of these bases their own power. So xy to the power of n becomes x to the n, y to the n. And likewise, if you're raising a fraction to the power of n, you give the numerator and the denominator their own fraction. So for example, x over y, all raised to the power of n, simply becomes x to the n over y to the n. Okay, and there's another example. If you've got x divided by y to the power of 2, it becomes x squared over y squared. Simple as that. If the bases don't match, just distribute the power. X to the minus n, division. What do? You see the negative power, it becomes 1 over x to the n. You divide it by what would be the multiple under normal circumstances. And finally then, as I told you in the previous slide, if you have a fraction in your power, the family of fractions you're dealing with, if they're halves or quarters or thirds or sixths, that will tell you what root to use, and you leave the numerator of that particular fraction with the base number. Okay, so here's an example. X to the 2/3. What do? Look at the family of fractions. It's 2/3. So the family is thirds, so that's going to be the cube root of x squared. And that's the answer, the cubed root of x squared. Okay, or if you want to, you can apply the cubed root first and then square afterwards. The order of operations doesn't matter. If it's easier to get the cube root, as I did in the previous set of questions, if it's easy to get the cube root, get it and square afterwards. If it's easier to square first and then get the cube root, do it. Do whatever is easiest. And don't be afraid, fall back on this thing if you need to, okay? Because this is going to be a great help for indices. Okay, and as I told you already, in your tables on page, what did I say, 21. So page 21 of your tables, they list the same laws. Similar bases, different powers. Multiplication, you add the powers, keep the base. Dividing the same base with different powers, keep the base, subtract the powers. Bracket through the two powers, keep the base, multiply the powers. Anything to the power 0 is 1. Negative indices turn into division of 1 by the positive form of the index. 1a to the power of a fraction. Look at the family of fractions, see what the denominator is, because that's the root you're going to use. So this here would be the q root of a to the 1. If you want to put a 1 there, you can. If the fraction is p over q, it's still going to be the q root of a to the p. If the base numbers are different, you may distribute the power to both bases in multiplication, and likewise with division. If you're dividing different bases raised to a power, you can simply distribute the p to both the numerator and the denominator. The best thing to do is to practice these things. Practice, practice, practice them. Get to know what rules to use. But for God's sake, have page 21 of your tables open with you when you're dealing with indices so you can see what rule to use. Okay, let's take a couple of examples here. Which of the following is equivalent to 2y to the power of 2 over 3? Now, be careful, okay? There are two things here that you have to remember. First of all, 2y to the 2 over 3. Because the 3 is over both of these, you may distribute the 3 to both. So that becomes 2 cubed multiplied by y to the 2/3 cubed. That's one of the rules, okay? If you're multiplying different bases, you may distribute the power to each base. 2 to the power of 3 multiplied by y to the 2/3. Now, 2 to the power of 3, that's 8, okay? Y to the power of 2/3, think about this. The bracket is in between what? The bracket is in between 2/3 and 3. If you're dividing by 3 and multiplying by 3, it's just going to leave you with y squared. So 8y squared is the answer, which is part A. Okay, next one. Simplify. X to the power of 0 multiplied by x to the power of 2 all raised to the power of 3 divided by x squared times x to the half. What? Yeah, bit by bit. Take it easy. Let's do the first one. Rule number 1. Anything to the power of 0 is 1. Okay. Rule number 2. If you have powers separated by a bracket, you keep the base and you multiply the powers. That's x to the 6. And then in here, you're multiplying the same base, so you keep the base and you add the powers, 2.5. That's it. So now you're multiplying these two and you're dividing these two. And by the way, when you multiply anything by 1, stays the same. So therefore, you've got x to the 6 divided by x to the 2.5. What does the rule say? If you're dividing the same base, you keep the base. And what is division related to? Division is related to subtraction. 6 minus 2.5. Well, 6 minus 2 is 4. Minus a half, that's 3.5. So there's the answer. X to the power of 3.5. Now that's where you start to use the rules. But you notice that I use them as I need them. And I take questions like that are fairly long. I take them in chunks. That's the best way to do it. Let's try this one. X to the power of 3 divided by x to the power of a half. Let's do that bracket first. Division of the same base. Keep the base, subtract the powers. 2.5. Okay. Multiplied by. Do what's in here. That's x to the power of 3 over 2 divided by x to the power of 0. Hold on a second. X to the power of 0 is 1. But when you divide anything by 1, it just stays x to the 3 over 2. And lastly, times x to the 7. Now, x to the 2.5 multiplied by x to the 3 over 2 multiplied by x to the 7. You're multiplying the same base. So you keep the base as the rules tell you, and you add your powers. 2.5 and 1.5 is 4, and 7 is 11. So there's your answer. x to the 2.5 multiplied by x to the 3 over 2 multiplied by x to the 7. Because the base numbers are all the same and you're multiplying them, you keep the base and you add the powers, because addition is related to multiplication. And the answer is x to the power of 11. Last one. What's the cubed root of 5 to the power of 15? Now watch. What's the cubed root of 5 to the power of 15? Roots are related to fractional indices. So if you're getting the third root, that means you can write this as 5 to the power of 15 over 3, which becomes 5 to the power of 5. And 5 to the power of 5 is 5 by 5 by 5 by 5 by 5. Now just this reason I'm writing this because sometimes you can see this in your head. 5 5s, 25. 5 5s, 25. 25 squared, 625. Bring down the last times 5. 5 6s are 30. So therefore that's your answer. 3125. You don't even need to do it in your calculator. You just need to know in and around where the answer is going to bring you. So it brings you to 3125. And again, there's plenty of online practice questions there that I would ask you to go through when you get these slides, and just make sure that you review all the time how the three ideas of a positive index leading to multiplication, a negative index leading to division, and a fractional index leading to roots in terms of the base number. Okay, so it's your turn. I'm going to leave this over to you. I'm going to ask you to go to your textbooks on page 178, 179 and answer those questions that are there. They follow exactly the same format as the questions that are gone before. Please have page 21 of your tables open, because the rules will be in front of you, and apply the rules to the questions that are given. Question 10 on page 178 and question 13 and 17 on page 179, and only do the bits that are marked. The bits that are marked here, because they will follow what I've been doing over the last couple of slides.